Stage our next speaker virtually, Jean-Paul Biberian.
So hello everybody. I'm not very far from you guys. I can almost see you from my balcony, but I'm tested positive to COVID. I'm looking always for situation where I am positive when there are reactions, but here I am positive to COVID. Anyway, okay, I'm going to talk to you about a very interesting project we are having in Europe, in the Clean HME project, and we have produced excess heat in nanoparticles of nickel alloys in hydrogen. And the interesting point here in this presentation is that we have been able to manufacture nanoparticles a different way of what has been done so far. So can I have the next slide, please? Okay, I will do an introduction. Then we have to go to the calorimeter, but calorimeter is very important in order to do good measurements. Then we go to the powders. Actually, the powder is extremely important. Then we see the excess heat, and we have a look to the reaction mechanism, because it's important at one point to know what's happening in the material. And then we conclude. Next slide, please. In the framework of the European project Clean HME, we have been working on experiment using nanoparticles made of nickel-based alloys, basically nickel and copper. These nanoparticles are of prime importance because previous work dating back to the work of Professor Arata using palladium nanoparticles embedded in zirconium oxide showed excess heat with only heat as an excitation. And I like that because it's a lot more simple for application. In order to measure accurately the anomalous heat produced, we used a CIBEC type calorimeter capable of going to very high temperature, up to 1000 degrees, with low heating power and good resolution. At Takahashi and the Nano team in Japan, they have made nickel and copper alloys also with the same technique as Arata was doing, and they have produced excess heat with hydrogen and deuterium. We have also developed a new method to fabricate the nano powder that I will go through very quickly, and the procedure to activate it. And there will be a slide also on the experiment with nickel deposited on carbon. Okay, next slide, please. Next slide, please. The calorimeter. Okay, it's a CIBEC type calorimeter. That means we are using 50 thermocouples placed in series so that you can measure the heat flow that way. It's something very well known, very precise, but we have adapted the design so that we can go to high temperatures. The basic design is a stainless steel 150 millimeter long by 63 millimeter in diameter vacuum chamber, inside which we can put quartz cells, different dimensions. Typically, I use 90 millimeter long and 20 millimeter in diameter, but we could use these different types of cells also if necessary. The quartz cells are heated by a Cantar wire wrapped around it and covered by a cement to isolate it. We put also 3 stainless steel screens in order to lower the heat loss by radiation, because we are in vacuum and the only heat loss we have is mainly radiation. The vacuum chamber is placed in a double wall aluminum cylinder where the 50 type K thermometer are placed in series, and the whole calorimeter is placed in a constant temperature water bath. And we have reached more than 1000 degrees C. Okay, next slide, please. Okay, this is a cut view of the system. You can see what I was describing. From the outside, you will see the 50 thermocouples in series. And then inside, you see the cell, the quartz cell, and the 3 screens. And that's all you have to see anyway. It's not very important, the details on that. Next slide. Okay, this is the construction of this calorimeter, where you can easily see the 50 thermocouples that are glued by cement on the both sides of the two aluminum cylinders. Next slide. Okay, this is the vacuum chamber I was talking about, 150 millimeter by 63 millimeter in diameter. Next slide. This is one of the quartz cells where you don't see the inside, but there is a Cantal wire and there is a cement on top to isolate it. Next slide. This is the full view of the system. It is placed in a constant temperature bath, water bath, to have good conditions. You know, it's important to have constant temperature bath in order to make good measurements. Next slide. Okay, this is a view of a 2 centimeter quartz cell and another one a 3 centimeter quartz cell. Next slide. Okay, we have done a calibration because it's important to have good calibration. The calibration is made with alumina powder and hydrogen, and you see that the precision of the calorimeter is pretty good, better than 100 milliwatts up to high temperatures. So this gives us trust on the measurements. One of the problems we have, if the room temperature changes a lot, and my lab is in the south of France, so in the summer it could be very hot. So if it is too hot, you can have some errors added to that, depending on the temperature between the day and night. Next slide, please. The powder. The powder in this experiment is being patented. How come I have the wrong slide? Okay, no, well, okay, let's go back to the one before. Somehow we have uploaded the wrong slide. That's okay. It's a hydroxide. It's a chemical compound. We have patented yesterday, so it's very new patent, you know. It's hydroxide. The hydroxide is a compound containing magnesium and aluminum as metals. This is a green powder. When you replace magnesium by nickel or copper, then you can, when you heat it up in air, if you heat it up in air, it becomes brown at high temperature. But if you heat it up in hydrogen, it becomes black and becomes magnetic. Before that, it was not magnetic. You need hydrogen to make it magnetic in order to reduce the oxide that's at the surface of the material. The next slide, please. Okay, at room temperature, nickel doesn't absorb hydrogen. You have to go to very high pressures. So in order to introduce hydrogen in the nickel, you have to heat it up at least at 200 degrees C. Then hydrogen will go inside the nickel. If you have also to remove the oxide layer, because if there's an oxide layer, then you cannot introduce the hydrogen inside the nickel. Therefore, it is necessary to remove the oxide layer first by heating in hydrogen, and then to put hydrogen in it at high temperature. So these two mechanisms can be performed simultaneously at the same time. Let's say. Okay, the next slide, please. So the experiments have been done, these 2 centimeter diameter cells and 3 centimeter diameter cells. The powder can be treated in a separate furnace before to prepare the powder, or in the reactor itself. The problem with doing it in the reactor itself is that the initial powder is very, very light, and when you use the vacuum pumps, the powder is pumped out, you know, as well as the remaining air. So it's better to prepare it outside and to put it in the reactor later on. Okay, next slide, please. Okay, so what to do? The calorimeter, the initial powder is heated under vacuum up to maximum temperature of the experiment, and then cooled down to the room temperature. Why do we do that? This is good because that also helps as a calibration of the system, because there's nothing active, so the calorimeter can be calibrated this way. You know, the calorimeter doesn't give you exact power. You have to calibrate it before. In this experiment, the calorimeter heated by steps of 5 to 10 watts, and the the time for stabilization is weighted. It depends, could be a few hours in order to have the stabilization, the complete stabilization, because the inertia of the system is pretty large, so you cannot have instant variation. So we wait for the 50 thermocouples give a stable signal. So hydrogen is introduced at room temperature, and the cell is heated by steps up to the maximum power. And at the maximum power, the cell is pumped down, and the power is lowered by steps again. Heating an hydrogen and cooling under vacuum is repeated until the excess heat is stabilized. Now, it's the maximum duration of an experiment is about 4 days. Okay, next slide, please. Okay, this is an example. So this is the final state, when we have stabilized everything. We do the heating, cooling, heating, cooling, heating, cooling with hydrogen and vacuum, hydrogen and vacuum. And this is a nickel-carbon ratio of 7:1. The weight was 7 grams, and 9 cycles were done under hydrogen. Next slide, please. Out of that, we can calculate the activation energy because we have the excesses versus temperature, so you can evaluate it's not very precise, obviously, because of the error bars, especially at low power, but that gives you an idea of the activation energy, which is not very different of what Ed Storms is measuring. Next one, please. I will pass a bit faster now on this experiment because they're about the same. This is a different one, nickel copper again. Next slide, please. Okay, another activation energy, slightly different number, 1.2 electron volts. Next slide. Another curve, but this one is with pure nickel. And you see a lot of good results. Next one. So another activation energy for that one. Next one. I will show you 6 of them, so be patient. This one, for some reason, there is a maximum in the production of heat. I don't know why, but that's happened a couple of times with pure nickel. Next one. And again, you can calculate the activation energy. Next one. Next one. Next one. Okay, you can see again, we can measure the activation energy of this experiment. And next one. Okay, this one is pure nickel again. Next one. Okay, the activation energy. Next one. Okay, this is a different one. This is nickel deposited on carbon particles. And we have done the same kind of procedure, heating and cooling, and 6 cycles. And you see also we observe excess heat. Next one. Okay, the activation energy here too. Next one. Okay, now okay, we have shown that we have excess heat. Now, what's the reaction mechanism there? Experiment with hydrogen exclude the formation of helium because it's difficult to do that with 2 hydrogen atoms. Looking for deuterium by a 3-body reaction is possible, like H plus E plus H, but difficult to measure in a hydrogen environment. The other option, with a low resolution mass spectrometer. The other option is to look for transmutation products. In one of the experiments, the CR92 experiment with pure nickel lasted 4 days in a continuous mode, but also produced heat during the previous cycles. When we were loading and deloading, it was producing excess heat also. We estimated the total energy produced like 3 to 4 megajoules. the amount of nickel in the powder is about 0.5 moles. And we have measured by SCM and 2 times, plus I will show you later by ICP-MS, the formation of copper. So it's very surprising that we have copper, but this is one of the mechanism, the possible mechanism, like a proton in the nickel would give you a copper. So the next slide, please. Okay, this is a view of the powder after. You see the grain size. With the next slide, we see a better resolution, maybe. Yeah, you see this is about 10 to 20 nanometers size of the nanoparticles. It's slightly bigger than what Arata was showing. He was showing like 5 nanometers. Next slide. The problem that we didn't have, we have shown that there is excess heat, but we have not shown that this copper is probably due to contamination, but we don't know. To have better results, we know that the excess heat increases very quickly with temperature, so it's good to go to higher temperatures. And at one point, it will be necessary to compare to deuterium to see if there is any variation to that. So thank you very much. Next slide. So okay, I think we have time for questions, maybe.
Jean-Paul, I would like to know if you've looked for tritium. You're using light hydrogen, which, according to my model, makes deuterium, as you indicated. The deuterium would then fuse with the hydrogen, making tritium. So I would like to know whether you've seen a growth of tritium in your cells.
No, I mean, Ed, we didn't look for tritium at all because we are not equipped to do that at this point. We don't have the mass spec for that or the equipment to do tritium measurement. I didn't work at Los Alamos before coming here.
It might be a little easier to see than transmutation.
I agree. I have to go to Los Alamos for a few days to learn that.
So, hey, Jean-Paul, thank you for your time. We are out of time for today.
Thank you.
Thank you again for your time.